is Bhavana Lalchand. She's coming to us from National Central University in Taiwan, working with Wenping Chen and Poshi Chiang. And we're going to be hearing about X-ray brown dwarfs in IC348. So after you.
Thank you. So as Steve introduced, my name is Bhavana Lalchand. I'm doing my PhD in Graduate Institute of Astronomy. And we are a part of a large program group with JCMT. And so we study one of the regions, which is IC348. And so I will be speaking more about it in detail. So to start with, I would be giving an introduction about IC348, and then I would be introducing about X-ray brown dwarfs, and also about observations of brown dwarfs in the cluster region. So what is the main purpose or the scientific goal behind the whole thing is about to study brown dwarfs in the formation stage or in the evolution stage, and also to study about the X-ray mechanisms. So, and to study in detail about the magnetic activities between, that is the transition between the late M-type dwarfs to L-type dwarfs, and also to know what is the coldest atmosphere required to sustain the dynamo mechanism. All right, so IC348 is basically, this is the infrared, far infrared image. And so here is the southwest region of IC348 where the current ongoing star formation is going on. And this is the main cluster region. And it hosts about 478 young stars. And the distance is about 300 parsec. And it is about 3 million years old. So to study about, to know the basic difference between stars, brown dwarfs, and planets, why brown dwarfs are pretty much interesting topic for me to know more about it, is we know that stars, they have sufficient mass to sustain hydrogen fusion, but whereas brown dwarfs, they do not have that. What happens in brown dwarfs is that they are more of lithium deuterium fusion, but not hydrogen fusion and no fusion at all for planets. And here I've just shown a picture to represent what or how a brown dwarf, a difference between a brown dwarf, Luma stars, and other planets. Okay, so this is the famous HR diagram. So in order to know the magnetic activity happening in which phase or where exactly at HR diagram, we would know that it is basically between F-type to M8 or to M type of brown dwarfs, whereas we would be seeing in detail what, why is it we do not see much in OBE stars or HEBE stars. Yeah. So in early OB stars, the X-rays is due to the magnetic, due to shocks, which is due to which it becomes unstable. And then we see that the X-ray luminosity of OB star is around 10 to the power of 7, -7. Whereas for Herbig AEB stars, the emission is very much soft. So we do not see that much. And that's the reason why it's quite similar to the classical Titori stars. And the value or the bolometric luminosity with respect to X-ray is between the range of -6 to -5. But whereas for a sun, it's between -7 to -6. But when it comes to mid-F to late M type solar stars, we see that it is between -7 to -3. And that depends mainly on the rotation rate. Whereas for old type brown dwarfs, we see that they are not steady X-ray emitters, either due to their neutral photospheres or there is no heating, and due to which we do not see any electrical currents there. And our sources, that is sources in IC348, the range is between 10 to the power of -5 to -4. Basically, this is just to show or to compare our sources with other young YSOs or with other sources to see how we can compare IC348 with other substellar objects. So I get data from CFHT Biocam. So we are a part of a team called as W-band, which hunts or looks for brown dwarfs. So we use a filter which is 1.4 microns, which is specially for water absorption. So we use CFHT, Gemini, and other telescopes to look for brown dwarfs. But whereas we use also JCMT and Scuba 2 images, which is 850 and 450 microns, to trace molecular clouds. And I use X-ray sources, which is archive X-ray sources from Chandra and XMM Newton. So I would speak about JCMT data analysis. So right now, what I have is 13 epoch, which is co-added in 850 microns. And then I use various other algorithms in order, here I use clump find algorithm to identify the peaks so that I can measure the peak sum and the total flux and the peak of my clumps. So in order to do that, I find the sky fluctuations. So I select blank regions in the sky or blank patches. And then I measure the sky value and the standard deviation. And depending upon that, we plot the contours and to see where our X-ray brown dwarfs correlate with the molecular clouds. Okay, so this is how it looks like, IC348. And so we went and, so I basically went and did a literature survey to find out to compare our source with the one that is published in literature. So I used, so I studied a paper of Emily Curtis, where if you see, there are a few underlying small detections of clumps that we see. Maybe it's because our is more sensitive when compared to the one that is published in the literature. And of course, JCMT has one of the deepest images that we can find so far. So these are the sources that we, so there are around 23 sources which was published or as a catalog when I run clump find algorithms. So these are the sources published by, sorry, the last one is not seen, published by Emily Curtis or Curtis et al. So I compare them with mine. So if you see, most of our sources or most of my sources do match over or do, or it is detected, I mean, I do detect all the sources found by Emily Curtis. So which is a good sign. Of course, there are a few where there is a slight deviation, but that's okay. As far as the source is present, we are happy with it. So Curtis et al., she used Scuba 850 micron maps to find, and she also, the range or the data nights is between 1999 to 2003, whereas for our JCMT is between 2015 to up to now. So we have totally 18 epochs of images. And so the typical value, RMS value that was chosen by Curtis et al. Was around 35 millijansky per beam. But for IC348 at present, we have around 10 millijansky per beam. And the lowest contour level that was set by Curtis et al. Was around 4 sigma RMS. And even my value that I set was around 4 sigma RMS. So when I compare that with Curtis et al. Paper, so I selected bright regions in the, so these are my regions that I selected, A, B, C, and D. So for now, for experiment purpose, we have selected C and D because A and B being an extended source. So I have tabulated the values that I have between, and I compare that with Curtis et al. So if you see our sources, well, right now we are comparing just the peaks. our sources is almost within the 10 to 20% of range. So we think that it's okay. Where we are going, where we are heading is probably correct. But it might not be that that good to compare the sum, especially because we do not know how the data was processed and what was the criteria set by the algorithm. So we are not quite sure about that. So, but when it comes to the peak, yeah, so we can say that yes, our values are almost within the 20% range. So I plotted a light curve of all the epochs. So right now I have 13 epochs. So it ranges from 1 to 13. And I have also shown you the values that I have chosen. So in this light curve, we cannot say much because it looks more like a randomized noise rather than a signal or rather than a proper peak. So we compare also, I mean, I drew a light curve also for region D. There are some sources which reach 3 sigma detection, but again, it looks more like noise. We cannot say much with this light curve of how the source varies from epoch to epoch. Either the variation is not that much, or maybe this light curve doesn't say much of how it varies from epoch to epoch. So this is a DSS optical image of IC348. The next thing that I do is I plot all the X-ray sources which I get from the archive of Chandra and XMM. And then I plot all the confirmed brown dwarfs found in IC348. And then I also plot the candidates of IC348. And then I plot the JCMT contours that I have generated. And if you see this particular source here, 1, this is a companion. So these are 2 brown dwarfs. And over here, which is a confirmed brown dwarfs, they are found to be embedded in the molecular cloud. So when I zoom in, if you see, you can see clearly now over here, a confirmed brown dwarf, which is, and we can say that as an X-ray confirmed brown dwarf, and also the candidate. So in total, right now, I have 4 brown dwarfs with 1 confirmed and 3 candidates. Next, we also plot YSOs. So there was a recent paper published by our team, led by Greg, who is the PI, co-PI. And so we map all the YSOs in IC348. So there are around 300 plus YSOs found. And so these X crosses, they are class 0, class 1, or flat spectrum YSOs, and the rest are all class 2 and class 3 YSOs. So next, I also compared, or I have listed out the embedded X-ray brown dwarfs that we have found so far. The 4 X-ray embedded brown dwarfs. So if you see their luminosities and their X-ray luminosity, it varies between 28 to 29, which is quite similar to the classical Titori stars as well. So there are, so Pravish, sorry, I would say Stelzer, he has found, or they have tabulated various substellar regions that they have found so far in these clusters. So if you see IC348, and between my values is almost the same, which is 28.2, and even the LX L-ball value is almost, that almost matches with what I have arrived. And so they have used Chandra. So yeah, this is just to show you that where are the other regions where they have found substellar objects emitting X-rays. This is just to show you how X-rays, of how they have studied X-ray emissions. So if you see, these are the light curves of various X-ray brown dwarfs. 1, emitting flares, and secondly, they measure in 2 ranges: soft band X-ray and also in hard X-rays. So if you see here, we see more of soft X-ray emission. So there are certain light curves which also emit, or they have seen a hard X-ray light curve, and it is predicting that it is quite similar to the solar flares, because even in solar flare, initially we see X-ray, soft X-rays coming up, and then later the hard X-rays. So moving on to the X-ray activity in M-type to L-type dwarfs. So between M4 to M8.5, there is a saturation type rotation activity. And whereas in M9 to later L dwarf, it is not quite clear of how or why the X-ray activity ceases, but it is given that, or it is said that it is due to the damping of magnetic energy, which is responsible for to support a chromosphere. And also the dust in the atmosphere of late M to early type, the grains, they begin to settle down after a temperature of 2000 Kelvin, and due to which of that settling down of grains also, they believe that the X-ray activity seems to be stopped, or it ceases. And we will be seeing in detail about the models, atmospheric models that they have predicted so far by Allard. And the model comes in 3 flavors. First is that no dust forms in the atmosphere, whereas so there are no dust grains allowed to form. And the second one is a dusty model, for which the temperature range is between 2500 to more or less 3200 Kelvin. So over there, the grain forming molecules are there, and even opacity. So due to which the dust forms and they remain suspended in the photosphere. The other model is condensed dust model. So the author is in more favor towards the condensed dust model, where there is a depletion of grain forming molecules, but they do not contribute to the opacity, and also the formation of grains, and they settle below the photosphere. So here you would see the clear example or state of how here we have effective temperature and the spectral type. So there is a break between after M8 when it starts with L0. So here you can see that the temperature drops down, and we can see a clear transition between M to M8, and then from M9 to later early or later type L dwarfs. Yeah, so there are various reasons for which we study. One is we study about the rotation rate. We also study about the effective temperature. So the rotation rate, we see that there is a saturation at type of rotation where it ranges between V sin I to be 3 or so, 3 kilometers per second. So here if you see V sin I, this gray symbols, they are all for M4 to M5 dwarfs, whereas this black open circles, they denote M5.5 to M6.5, and these black filled circles, they are M7 to M8.5 dwarfs. So they have a typically V sin I to be around say 15, and over here they have also enlarged it, and we see that the gray symbol over here is from M4 to M8.5, and then the black open circles is M9, and M9.5 to L dwarfs are these circles. So if you see, as it goes further, the V sin I keeps on increasing, but we are not sure whether once it becomes a fast rotator, whether the X-ray activity ceases because of that. So we have, so here if you see, there is a spectral type versus log Lx by L whole. So these are all the M-type dwarfs which are obtained from the archive. And this work over here, you can see these are all the marked, or these are all the brown dwarfs that they have studied so far. And these are from the literatures. So this is the this is the saturation type slope, saturation activity slope, where after that you do not find much of a difference. So this slope is obtained from this formula, where SP is nothing but the spectral type. And so from here we calculate the Lx by L-bol to be -3. And this is the detection limit for Chandra, which is 3 sigma. And these are the X-ray flares. So here you can see X-ray flares, and this connection is to the quiescent phase. So all these dashed lines is just to connect the quiescent phase and the X-ray flare phase as well. So we do not see much after M9. It's quite clear, or it's quite evident that after M9, the X-ray activity seems to reduce, or it seems to stop. So the reason, or which they believe, the implication is that the charged particles, they get soaked up by the grains, and due to which they become more massive and larger, and also due to which these particles, they become quite neutral, and this causes the current dissipation, because of which they enter, or they are called as cool roves, and that happens even when the grains are not present. And the another thing is that the magnetic field, that is, they derive due to the angular momentum. So when that spins down, or when angular momentum goes down, so the momentum that is required for the magnetic field seems to be doesn't seem to be there. So, however, we find that the atmosphere decreases with later type, and that main reason is due to dust formation, or due to the combination of neutrality and dust formation as well. So so here we see that the angular momentum is being suppressed, and it is due to which we say that it could be expected to be a fast rotator after M9 type dwarfs. So I conclude by saying that we would like to further investigate the X-ray brown dwarfs, and we would like to study about their flux, their mass density using the 850 microns and 450 micron maps. And we would also like to have a better understanding, or probably design a model to study more about X-ray activity from mid-M to L-type early dwarfs. Thank you.
So, well, thank you so much. Does anybody have any questions?